If someone were to ask me why it is that we need causal knowledge, the shortest informative answer I could give is to predict the results of policy interventions. Over the past 20 years, this simple idea has transformed the way causation is discussed in philosophy, and interventions are at the core of the graphical causal modeling approach I've been discussing in these videos. But this raises as many questions as it answers. What is an intervention? And shouldn't we still be able to talk about causation in contexts where humans can't intervene? Today I'll answer both these questions and explain how causal models predict how the world will change as a result of interventions. Hello, and welcome to Causal Foundations. I'm Naftali Weinberger, a philosopher of science who's been researching causal models for over a decade. In this series, I introduce foundational concepts from causal inference in videos of approximately 10 minutes. In previous episodes, I introduced directed acyclic graphs, or DAGs, in which the nodes are random variables, and the arrows are direct causal relationships. The direct causes of a variable are its parents. The variables in a DAG have an associated probability distribution, which gives the probabilities of any combination of variables conditional on any others. Now, you won't absolutely need it, but if you want to develop a deep mathematical understanding of what follows, the following feature of probability theory helps. Given a probability distribution over variables x1 to x3, you can decompose it into the probability of x1 given x2 and 3 times the probability of x2 given x3 times the probability of x3. This is called the chain rule, and you can apply it in any order. Now here's something interesting. Given a causal graph, we can give a decomposition in which each variable is given conditional only on its parents. So while the chain rule would decompose x2 to x3 like so, given our DAG, we can replace the probability of x2 given x1 with just the probability of x2, since x1 is not a parent of x2. That such a decomposition is possible is one formulation of the causal Markov condition from episode 7, which makes precise how each variable depends only on its parents in the DAG. The focus of today's episode is the Manipulation Theorem, which allows you to determine how a probability distribution will shift as a result of an intervention. Consider the effect of social media usage on depression among 14-year-olds, and suppose the sole common cause is the quality of their real-life social network. What we want to know is the effect of social media on depression, which corresponds to the effect of intervening on social media, so that it no longer depends on its direct causes. This might involve a ban on social media use for teenagers. A maximally effective ban would be represented as breaking the arrows into the cause, and corresponds to the probability of depression given do social media. But in the world as it actually is, social media usage does depend on social network quality. So why think that the result of the intervention is relevant to understanding this causal relationship in the world when we don't intervene? Instead of envisioning someone who intervenes to break the arrow into the cause, imagine someone who observes the agent who is intervening. From this outside perspective, we can include a variable for the ban, such that when its value is 0, the other variables have their non-intervention distribution, and when it's 1, they have their intervention distribution. So conditioning on ban equals 0 yields the non-intervention DAG, and conditioning on ban equals 1 yields the intervention DAG. The intervention that breaks the arrows in the top graphs gets represented as conditioning in the expanded graph. I'll use the terms intervention and manipulation interchangeably. We label the three graphs as the unmanipulated graph, the manipulated graph, and the combined graph. The variables in the combined graph get partitioned into those that were in the original graphs, and the additional variables in the combined graph. The variables added to the combined graph are called policy variables, and they need to be exogenous, which means that they're not effects of other variables in the graph. Finally, the manipulated variables are the direct effects of the policy variables, assuming the policy variables alter the distribution. Here, social media usage is the only manipulated variable. The manipulation theorem says that you can calculate the manipulated joint distribution as follows. For all the variables that are manipulated, their probability is whatever it is conditional on their parents in the manipulated graph. For all the variables that are not manipulated, their probability is whatever it is conditional on their parents in the unmanipulated graph. The manipulated joint distribution is the result of multiplying them together. While the notation can get clunky, all this is saying is that when you update the distribution post-manipulation, you only need to update the manipulated variables. The manipulation theorem only requires that interventions be exogenous, not that they break arrows. An intervention won't break the arrow if the manipulated variable still depends on its prior causes. But the theorem will still tell you how to derive the manipulated distribution. Arrow-breaking interventions that fix the value of a variable independent of its other causes are called hard interventions, and these correspond to the do operator. In contrast, interventions that merely change the probability distribution of the intervened upon variable are called soft interventions. If the social media ban reduced social media usage without eliminating it, it would be a soft intervention. Although hard interventions are especially effective at identifying causal effects by breaking all backdoor paths, sometimes only soft interventions are available, and these can still aid causal inference. Instrumental variable methods in econometrics aim to identify effects by finding variables playing the role of soft interventions. The idea that causation is closely bound to our ability to intervene has great intuitive appeal. Our most basic experience of causal efficacy is through our actions in the world. Long before modern science, humans and other primates gained survival advantages by learning to manipulate their environments. In fact, it's well documented that babies and toddlers are able to acquire causal knowledge by observing and performing interventions. But the big worry about using interventions to analyze causation has been that this would make causation dependent on human concerns. We can say that an asteroid caused the dinosaur extinction without appeal to human agents. So clearly what causes what can't be reduced to facts about human agency. The manipulation theorem reveals that the interventions employed in causal analysis apply not just to human actions, but can be given a general formal characterization that makes no appeal to agency. The theorem is a direct consequence of the causal Markov condition, which does not even reference interventions. The theorem thereby links causation to interventions without making causal concepts depend on human abilities. I'll end this episode with a philosophical question. The manipulation theorem reveals that it's possible to recast the interventions within a system as conditioning on variables within larger systems. Given the role of such interventions in defining causal relationships, does this mean that causal relationships only arise in open systems, meaning systems that are embedded within larger ones? The implication would be that it no longer makes sense to talk about causation with respect to closed systems, such as the universe as a whole. This question remains unresolved, and I'll return to it in future episodes. Even if causation only applies to open systems, that includes all systems outside of fundamental physics, and some of my colleagues have argued that even fundamental physics pertains to open systems. For the moment, I'll flag this as an example of a foundational question about causation that emerges from thinking about causal methodology. Thank you for listening. If you made it this far, please don't forget to like and subscribe. The manipulation theorem comes from Causation, Prediction, and Search on page 51. The formulation is rather convoluted, but this episode gives you all you need to understand it fully.